As we continue through 6.4, now that we've learned a new derivative, that leads to new antiderivatives. So we had log of u has a derivative 1 over u du, or again, if you prefer, du over u, whichever way you prefer to see that. But now that opens up an antiderivative. But here is an issue. From what we had, especially if you go back to that original one with the simple x instead of u, well, from what we were given, the anti of 1 over x would give me log x. And that's basically right, but we have to realize we've got an issue that's coming up here. So there's just going to be one little extra piece that needs to go on this line. Take the derivative, log x gives you 1 over x, so again, it seems right, but remembering how definite integrals work, that if this is a definite integral, well, we have to make sure we don't have any discontinuities on that interval. This would have a discontinuity at 0, so we have to avoid that. But if I had the integral from 1 to 3, well, that works. Then it would be the log from 1 to 3. But if I had the integral from -3 to -1, that still makes sense. That still avoids the discontinuity, so I can still apply the fundamental theorem, and it feels like everything is working, but watch what happens on the next line. Took my antiderivative, plugged in my top, minus, plugged in my bottom. Do you see something wrong here? Both of these are undefined. Both of these are does not exist. The domain of a log function is that the inner part has to be greater than 0. You can't have negatives. E to what power gets you to a negative? You never get to a negative. And that's not true with that's not just true with natural log. All logs have that issue. So remembering what this is telling us to find the area. So if we think about this for a minute, we could see how we work our way out of this little hole. So that if we have that's the basic 1 over x graph, this hyperbola that's split across the origin like this. And now again, as long as our area doesn't cross 0, both of these make sense. Find the area from here to here. That would be from 1 to 3. Or over here, find the area from -1 to -3 would be the area from here to here. Notice there's a lot of symmetry here. All of this already works. You do this one, that works, that answer makes sense. But look at the symmetry. The area here is the same as the area here, right? We've got odd symmetry here. So this piece that's above the x-axis is mirrored by this piece that's below the x-axis. So these are matching pieces. But the difference is this one is below the x-axis. So this answer should be negative. And if we finish this one, this would be log of 3 minus log of 1, and log of 1 equals 0. So this whole answer is natural log of 3. Come back here, this should be the same situation, just this answer should be negative. This is all fixed by when we take an antiderivative, including the absolute value on the argument. And that is not just a suggestion, it is a requirement. So that now it doesn't matter in any definite integral. Here, log of absolute value of x, well, when you use these values, absolute value of 3 is the same thing as positive 3. So you could almost get away with forgetting the absolute value here, but we still want to make that a habit to include the absolute value on the x or on the u generically. And now when we do that, now it all matches up. Because now absolute value of -1 is positive 1, so this whole thing is 0. Absolute value of -3 is positive 3. And now, as we said, these should have the same area, Just this one should be a positive answer because it's above the x-axis, and this one should be negative because it's below. That's all we needed. So I know I took a few minutes to explain that, but ultimately, that's just what it boils down to. Some people, they like to make this on their chart twice. They like to have a line for the derivative, and then they make a separate line for the antiderivative. If you want to, that's your choice. Mostly I find people just use this. When you're taking a derivative, you don't have the absolute values, but it doesn't matter. You could just ignore it and move to the rule, but for antis, that reminds you, you need that absolute value. That, again, is a must. Okay, so that gets us started. Let's jump in and let's see a couple of antiderivatives. Let's evaluate a couple of integrals. And just like we did in the exponential video, I'm just going to solve indefinites. Definites, we'll probably do one at the very end as a quick reminder of, definite integrals connect to area under the curve. But I'm really doing this to focus on the antiderivatives. Getting this new rule, making yourself used to dealing with it. Okay, so this first one may not be so obvious, but just a tiny little manipulation. 10 over x, you could kick the 10 out in front, and then that is 1 over x. So once we see that, if all we have is a plain x in the denominator, that leads to an antiderivative of log of x. Now number 2 is just going to be a tiny bit more than that. Let's look at the integral 5 over, let's do 2x minus 1. Again, some people, like we always say, there are some problems that are easy enough that people can fight their way without using U-subs. How do you end up with a 2x minus 1 in the denominator? You must have started with a log of 2x minus 1. The derivative of this would put the 2x minus 1 in the denominator, but then you get a times 2. We need to have a times 5, so I'm missing an extra 2.5 or 5 over 2. And that would be your answer. Most people would probably put the 5 over 2 out in front, but some people can fight their way through it. But for a lot of us, especially when we're first getting started, that's just a little bit complicated. Oh, you know what? Before we finish number 2, come back to number 1 for a quick moment. If you have a lot of good habits solving integrals, you probably wouldn't do this as your first move. You'd probably do something like this as your first move. And this is the point where I want to remind you that looks like power rule. But go back to our very first review video and remember, power rule, if you could bring your x to the numerator, that rule works for every exponent except when the exponent is -1. And that's exactly what we get here. It's tempting to push the 10 along, add 1 to the exponent, divide by that new exponent, but that's a whole bunch of garbage. But that's a good reminder. Some people, besides just making that little switch, some people also like to remind themselves that 1 over u is the same thing as u to the -1. Because a quick alternative, if this was the integral 10 over x squared, there is no logarithm in this problem. This does need this technique. This would become 10x to the -2 as a rewrite, and then that would use power rule. Add 1 to the exponent, divide by that new exponent, and that would be your answer. So that is a very natural move to try and bring the x to the numerator. But if all you get is an x to the -1, you can do that, but just realize you're going to natural log. That finishes the power rule. Every other u to an n, the anti is u to the n plus 1 over n plus 1, except when n is -1. Now we know what happens when n is -1. Now we've got an answer. So, now coming back over to number 2. So as we discussed, some people can, again, fight their way through it. Understanding, seeing enough derivatives makes them realize that this is going to be a part of it, and then fighting their way to get the right coefficient. But for most of us, that's a little complicated. And what do we do with a complicated situation? We use the appropriate U-sub. Now, two ways to look at this. Some people look at this little rewrite, and they see u to the -1, and one of the original ideas for U-subs is picking u as what's inside. So that would give you the idea of what to pick for u. But others, it's about making it work on your chart. And now we're seeing what's a possibility for u. Well, picking u as the entire denominator is a possibility. And if that works, this is what we'll be left with, so we can take a good antiderivative. And that's how a lot of people choose to do this one. They see a little bit of a tough spot. They can't bring this whole thing up, or if they do, now it's 2x minus 1 to the -1 power. And now they've just kind of swapped a little division problem to a little inner-outer problem. So u would be 2x minus 1, no matter which way you look at it. The derivative of u would be 2 times dx. Divide that over. My integral would be 5 over u, du over 2. There are no x's. The 5 and the 2, I could kick that out in front. Just again, keep track, 5 in the numerator, 2 in the denominator. And I'm left with 1 over u du. If we pick u to be the denominator, we should be celebrating when we get to here. That means we made a good choice for u. We're not finished. We still need the antiderivative, but now we're right on our chart. The anti of 1 over u du is log absolute value u. So the 5 over 2 pushes along, log absolute value u, indefinite integral, so this finishes with a plus c, back sub, and we're right back what we had here a moment ago. Let's do another. Number 3, let's take a look at the integral of, let's do 2x to the 4th over x to the 5th plus 10 dx. Now things are looking uglier. Things are looking a little bit more challenging. Here, not too bad, a little bit of a division issue. A U-sub can help us out. Now we've got a major issue with division. But one more time, stuck with division. What works? Well, trying u as the denominator is worthwhile. So let's try it. That's a situation that works here. You can't pick u from e to the u. There is no e in this problem. That doesn't even make any sense. U as the inner function, well, without any manipulation, people don't see any inner-outer function. If you bring this whole thing up to the -1, now you've got inner-outer. But for a lot of us, we leave it right here, and we just recognize u as the denominator might help us. And this one works pretty well. Du 5x to the 4th dx. As I always try and point out, I'm already feeling good. If I'm picking the denominator to be u, I'm concerned that that x to the 4th is going to need to cancel with something, and there's the x to the 4th for it to cancel with. I don't care about the 2 and the 5 reducing or not reducing. It's the x's that have to go. If you don't quite see it here, no shame, no problem. Make sure we see it on the next line. For the moment, this is hanging out. We pick that as u. dx, I solve this for dx, so this goes in as a clean substitution. And we see it does work. Is this a good u-sub? Well, these x's cancel entirely. I have a 2 over 5. Right before it was a 5 over 2, now it's a 2 over 5. Just trying to make sure we keep our numbers in the right spot. We don't pick what's on the top, what's on the bottom. It is what it is based on the problem. So that's out in front. I've got 1 over u du left inside. Celebrating. Here, I got rid of my x's. Not only, the big picture is, do you know the antiderivative of this? And you do. But along the way, did you simplify the problem? That ugly division we had is no longer there, and that little simple division, again, switching it to u to the negative 1 doesn't matter. It still leads us to an antiderivative 2/5 log absolute value u, and I back sub 2/5 log absolute value x to the 5th plus 10. Take a derivative to check, push this along, 1 over this times an extra 5x to the 4th, clean it up. You see it matches your original problem. No doubt at all, this is the correct antiderivative. Very quick, if this was x squared plus 10, the book sometimes takes advantage, something like x squared plus 10. It doesn't matter what you plug in, it would always be positive. So sometimes you'll notice the book will drop an absolute value and just use parentheses. They're not just dropping it, they're realizing for that particular expression, you don't have to worry about negatives. I don't think you have to worry about that at all. Just trying to point out the book does that occasionally. Okay, still a little more practice and still a few more points that need to be made. So we're on number 4. And for number 4, let's look at the integral 8x cubed minus 4x all over 2x to the 4th minus 2x squared plus 1 dx. Okay. Once again, still very messy, and I'm picking on just some regular variables, x's to powers. If there's trig functions and e's in here, that's just fine. Still the same thing happens. Messy division, no clear inner outer, u as the denominator is worth trying. Now at this point you might say, why does he keep saying worth trying? It's working. And that's fantastic, everybody, but you have to realize as we keep going, the further we get, the less reliable it is to just say, this is definitely the value for you. We have more possibilities that will present themselves, and they'll all be legitimate possibilities, and then we have to figure out which one works. Here, this is the only good possibility for you. But that's why I keep saying that, just to point out, we will get to a point where it's just a little bit tougher, okay? So, du, there's my u, the derivative, 8x cubed minus 4x, that whole thing dx. This is perfect. I mean, that matches exactly. Even though there's multiple pieces, completely matches. If this was like a 4x cubed minus 2x, we could do some factoring to make these things cancel. But this is going to be perfect. All this divides to the other side. This is hanging out. The whole bottom is u. This dx becomes du over the 8x cubed minus 4x. We've already noticed this cancels perfectly. There's not even an extra number. This is exactly 1 over u, nothing extra. So the anti is log of absolute value u. And I back sub. One quick point to make before I keep going here. Again, still have several other little things. We're getting the biggest thing. We're getting a lot of the big meat, seeing a new U-sub. Still got a few other little things to discuss. Number 5, let's look at a problem that looks awfully similar to number 4. We see how similar these two problems are? Both of them have trouble with division. But here, it's more division of simple functions, so we tried u as the denominator to try something, and it ended up working. But in the second one, in number 5, we're not looking at u as the denominator. I see division, but I see in a much greater, kind of looking at this as a bigger picture, I see as an inner-outer situation here. So it ends up with the same u. The u here will be the same thing that we use as the u here, but it's for different reasons. Here, trying u as the entire denominator, working. Again, whenever you pick u as the denominator, you are always working to exactly this. If there's any extra multipliers can go out in front, but u as the denominator has to get us to here to end up with log of an answer. But over here, you're picking this as u because that's the inner function. So when you go through and clean this one up with this u sub, you don't get 1 over u, you get 1 over u to the 5th power. Okay? So that is not log of u. This one, you still need to go back to traditional means, bring the u up by negating the exponent. Antiderivative is using power rule, and then I would back sub, and I would still, again, that was power rule. That's the point. We picked u. It ended up being the same u, but for different reasons. Here, u as the entire denominator led us to this, led us to log. Here, u as the inner function led me to this, which led me to power rule. Okay, one other quick thing to point out. Both of these, that multiplier out in front, I would not expect you to do anything more with these answers, but to realize multiplier out in front of a log, sometimes the book brings that in. I would not be surprised at all for this problem if the book wrote this as log, the 5th root of x to the 5th power plus 10 squared. Bringing that 2/5 in as an exponent, and then even more so, using the 2/5 exponent as a radical and regular exponent. If this was just a 2, it would just be this whole thing squared. So again, I don't mind, but just again, to point out, the book loves simplifying so that they consider contracting a part of simplifying their answers. Not necessary, but you definitely want to recognize that if you have this answer and the book has that as an exponent, to realize you have the same thing. Okay. So now we see all that. And now some people start to think to themselves, okay, u is the denominator. I got it. And now let's take a look at this problem. Even if that exponent of 5 is not there, and another quick aside, this and this are not at all the same thing. Here, that exponent 5 is on the variable x. That is inside the log function. Whatever your x value is, that is being raised to the 5th power, then you are taking the log. Here, whatever your x, that immediately has the log taken, and then that is raised to the 5th power. So very different here to point that out. And to realize, even if that 5 wasn't there, what I'm about to do would be the answer. If you think u is the denominator, because we've seen that work a couple of times already, realize u equals x is never going to work as a u substitution. If u equals x, then du equals dx, and you just change the variable and accomplish nothing. The point of a u sub is not just to change the variable, but to change the variable and get to something simpler. Whether it's something like this, which takes me to a log, or something like this, which now again, no crazy division, no crazy inner outer, just a simple variable to a power, which I could raise up and then use power rule. So the u sub is all about simplifying the integral. So sometimes you've just got to try something. This one at least works. U as log x at least makes sense because that's our inner outer setup. But if you just pick u as x, that's definitely not going to work. So you've got to try something else. So that at least has inner outer, but even if this wasn't here, it's something to try. Notice, log does not appear on this side. So we can't leave a log. In some way, we're going to need to get rid of it. So by picking the u as your log, that's one way to try and get rid of it and hope something good happens. And that's exactly what's going to happen here. Because if I pick u as log x, du is 1 over x dx, Dividing the 1 over x over is the same as multiplying by x. That x will cancel with that one. Let's see it. This has now become u to the 5th power. This is hanging out. But then dx became x times du, not dx. So those x's cancel. And the u has worked. Messy division that we can't divide, an extra inner-outer situation. We got to do something. We tried a u. This was really the only good choice for u. And now that we get to here, things simplified. There's no more x's. And this is something we could finish. Even easier than this one, power rule, u to the 6 over 6 plus c. So this answer is log of x all to the 6th power over 6, or a 1 over 6 out in front if you prefer, plus c. We still keep going, everybody. We've covered the biggest, the most important stuff, but we still have a few little details that need to be covered. Because now that we have this new idea for u-subs, let's realize we can add a little bit more to that ff prime chart. I'm going to make another fresh one. And we're going to realize if we go back, actually let me pull it out while I mention it. We've got a lot of known trig antiderivatives. But most of the antiderivatives involve some odd combinations. You need secant squared. Secant cubed, we don't know the antiderivative, but secant squared has an antiderivative of exactly tangent. Okay? We know the antiderivative of secant times tangent. But what if it's just secant by itself? As of right now, the only two trig functions we know the antiderivative of those exact ones by themselves are cosine and sine. All the others need a little more. But now, we're going to realize we can do something with that now. I'm going to put tangent and secant on the right side, and we're going to learn their antiderivatives. So I'm going to start off, even though I'm writing tangent u, we're actually going to start off with tan theta. Well, I want the antiderivative. I don't know what it is. So I'm going to manipulate. And how can I manipulate tangent? Well, I'll manipulate it into sine over cosine. Now, normally you would say, well, why would we do that? That seems like we're going backwards. This is one simple function. Now I've got division. But the problem is we didn't know what to do with tangent, so we had to try something. So I try this. Now I've got division. Well, that gives me a possibility for a u-sub to work. I pick u as the denominator. The derivative of cosine is negative sine. Sine hanging out. Cosine became u. D theta became du over negative sine. As we've seen, you pick u as the denominator, the signs cancel. Yeah, there's an extra negative, but you pick u as the denominator, you want 1 over u du. That's a known antiderivative. This u substitution is working. We finished the problem. That would be minus log absolute value of u plus c. When I back sub, I get minus log, and u was cosine. But here's a funny little issue, everybody. There are a few calc books that's what they say. Their rule for the anti of tangent is negative log of cosine, but most books take this a little further. Ours does as well. They take this minus 1 out in front and move it inside as an exponent. I don't want to write it right here. That looks like inverse cosine. So it's technically all cosine to the negative 1 power. But cosine to the negative 1 power is 1 over cosine. We've got a whole separate trig function for that. So the anti of tangent is log of secant of u. Nice proof, and that's kind of what this is. This is a proof, but now we have the result, and now we can use it. What I just did for tangent, you could do the exact same thing for cotangent. You'd have cosine over sine. That one even works out cleaner because you don't even get the extra negative. The anti of cotangent is log of sine. Okay? I'm not going to put it on our chart. We're getting a lot of new functions, so I'm going to try and keep the list down to a little bit of a minimum, but I definitely want you to realize that what we did for tangent, we're going to need this. This result is going to come up quite a bit in chapter 7. So we definitely want to get this on our list and start remembering it as a result. But to also realize we could do the same thing with cotangent. Secant is not quite as friendly, but I'll do some work for secant, we'll get a rule, and then we'll realize the same idea would work with cosecant. So if I start with secant, it initially feels like we do the same thing. Well, for tangent, I wrote it as sine over cosine. So for secant, well, secant is 1 over cosine. And now people go, oh, okay, well, now we try u as cosine. It doesn't work, right? U is cosine, but then du gets the negative sign. This is where if people don't keep track of their extra notation, they just force it like it works, and then this becomes 1 over u, and they just stick the du in, but that is not correct. So it was a worthwhile try, but that u sub is not working. So what else can you even do? It doesn't seem like there's anything obvious, and what I'm going to do is definitely not obvious. It just seems like I'm randomly picking this, and to be quite frank and honest with you, the only reason I know this is because it was showed to me. How somebody thought of this in the first place is really impressive, but now you'll see that it works. I take secant, and I'm just going to decide to multiply top and bottom by secant plus tangent. That seems like a real goofy stretch, but watch what happens. Distribute the secant on top. I get secant squared plus secant tangent, and it's all over secant plus tangent. Now, with this modification, I try u as the denominator. U is secant plus tangent. So du, well, the derivative of secant is secant tangent plus the derivative of tangent is secant squared. Do you notice why I'm pausing? In a very lucky coincidence, that's what I was saying. Where did this come from? Why do you multiply top and bottom by this? Well, I have to multiply top and bottom by the same thing, so it's a fair manipulation that I didn't just change the function. But why by this specifically? Because it works. You pick u as the denominator. This is exactly what we have in the numerator, so this cancels. You get 1 over u du. So the anti is log of u. And in this case, I'm just going to jump right to the answer. Log of secant u plus tangent u. That is the antiderivative of secant. So now we'll do 2 very quick problems pointing out how to use this. Now that we have the result, this is nice. I hope you're able to understand, realize that logs opened up some new doors for us, and that's how these work, right? Now that we're done with it, now we can check. Take the derivative of log of secant. We did that earlier. We did that in part 1. We got 1 over secant times secant tangent. The secant's canceled. So we've seen things like this already when we took derivatives, but now we've got the results written up. So now, see how we can use this. I'm going to take advantage by making this an area problem. Find the area under the curve, x squared tangent of x cubed from x equals 0 to x equal 1. Well, 2 things with this problem. Number 1, the reminder area under the curves are definite integrals. And I could do simple ones. I could just start off with what's the area under the curve, 12 over x, and that's just a simple log x. It's just the area under the curve. We need to set up a definite integral. Whether it's easy to find the antiderivative or it's complicated, that is just whatever it is based on the individual problem. But we need to be able to apply, okay? So I set up the area, just as that reminder, set up the integral. That's what will give me the area. But now I need to finish solving this. And this is a mess. Multiplication, inner, outer. There's no easy way to clean this up. We can never ignore those types of situations. Multiplication, division, that is never something we can just ignore. It has to be something that we perfectly know it's antiderivative, or we have to manipulate, use a U-sub, do something. So here, my U-sub, I'll pick U as the inner. So if U is x cubed, my du, well, there's my x squared, that'll cancel. I like to leave my bounds off until I see everything works. X squared, tangent of u, du over 3x squared. Okay, it's perfect. The x squareds cancel as I hoped. I've got a 1/3 out in front. Since the last time I had something like this, I pushed the limits. Let me not this time. But here's the big thing. Right now, that is the right U-sub. Even go back to Calc 1 when you first learned U-subs, you should have had that instinct to pick that as U, to see this is working. But in Calc 1, you would be stumped right here. You've done all the right things. Everything's simplified. There's no more multiplication. That inner-outer situation has been simplified, but we would just be stuck here because that's an unknown antiderivative. No more. Now we've got a rule to finish this. So now we celebrate. The U substitution worked. Simplify the problem. Secant of U. There's my antiderivative, right? Just from that previous page. Still would back, I'm sorry, wait, not plus C. This was a definite integral. And then as I back sub, so that'll be secant of U, so secant of x cubed, and I've still got my bounds 0 and 1. Plugging those in, 1/3 log of secant of 1 minus 1/3 log of secant of 0. If you keep going here, secant of 0 is 1 over cosine of 0. Cosine of 0 is 1. Log of 1 is 0. This whole thing actually does become 0. So that is good as our answer is going to get. But I'd be perfectly happy with that whole thing. Even if you stopped here, that is a pretty good spot. So again, realizing nothing really new here, just this last little piece. That initial U substitution, if I made this x squared secant x cubed, you do the exact same U sub. You get secant U, so the anti would be log of secant U plus tangent U. Both of them would have U's. You'd back sub into both of those spots. Okay, again, another pretty lengthy video. A lot that's gone on in this section. The biggest thing is, without a doubt, after you got used to the derivatives of logs, starting to do some of the antiderivatives, get used to U as the denominator, get it written in your notes, the new antiderivatives for plane tangent, for plane secant. And here's the very, very last thing, everybody. Save this for last. We're going to do this very quickly. I think you've got plenty as far as what you need to know. But with the derivatives and antiderivatives for logs and exponentials, we're really sticking with E and natural log. But we should still say, what is the derivative if it's not e to the x, if it's a to the x? Or if it's not natural log, if it's log base a? And it's pretty quick, everybody. I'll show you this really fast, just so you have it. I think there's one, maybe two problems in the homework, just so you could just practice a touch. But this is not coming up on any test or quiz. Just to realize this is for your information. Take the derivative of a to the x. Well, it's got to work the same way as e to the x. So it's got to repeat itself. But what's extra You get an extra times natural log of a. That's it. So e to the x is itself natural log of e, but natural log of e is 1. So that's why this general rule also covers the e to the x case. So a quick example, let's find the derivative of 4 to the x, and it would be 4 to the x log 4. If it was more than just a plain x, if it was 4 to the x cubed, it would be 4 to the x cubed log 4, and then you'd have your du at the end. You'd still have that chain rule. You'd still have to finish, take the derivative of the exponent. For an antiderivative, if I wanted the integral of a to the x, well, if the derivative has an extra times log 4, the antiderivative would have a divided by natural log of 4. That's it. That's all there is to it. That's all I want to say. Like I said, I just quickly pointed out chain rule here, but really just wanted to point out you get this extra times log a. Well, if you get a times log a in a derivative, the anti gets a divided by log a in it. Okay. Similar with log base a. This really relies on the change of base formula. Before I can take the derivative, let me change it to natural log. And realize that natural log of a, that's a multiplier. So what's the derivative going to be here? The 1 over log a is just out in front, and then you get your 1 over x. Or 1 over u du if there was more to it. But that's it. So an a to the x gets an extra times log a in its derivative. A log base a of x gets an extra divided by log a in its derivative. And we don't have to worry about antiderivatives here. Notice we didn't take an antiderivative of log. We took antiderivatives of 1 over x and ended up with logs.